All right, so an equilibrium solution is constant for all values of the independent variable. And you can see this on your slope or direction field where you have a horizontal line. So that graph gives you a horizontal line. So here I have a horizontal line, and here I have a horizontal line. So those look like they are equilibrium solutions. And we classify our equilibrium solutions as either stable or unstable. So we say it's stable if a small change in the initial condition gives a solution that tends toward the equilibrium as the independent variable goes to positive infinity. So as we go out this direction with our independent variable, does our direction field tend to direct us towards the equilibrium or away from it? So if it's directing us towards that equilibrium solution, then we would call that a stable solution. And we would say it's an unstable one if a small change in the initial condition gives a solution that veers away from the equilibrium as our independent variable goes out to infinity. Okay. So here, we've identified this is our equilibrium solution, and let's pick an initial condition and follow it. So I start here. This tells me to head off in this direction, so I do that. This tells me to flatten out a little bit, so I do that and head off some more. This tells me to really flatten out. So as t goes to positive infinity, this solution is heading towards my equilibrium here. Okay, and I can pick another. So it says a small change in the initial condition. So let's just move a little bit further over. So here, and this one tells me to head off at this direction, and as I get here, it tells me to flatten out. So yeah, this is also heading towards my equilibrium. Maybe pick one here. So it tells me to head in this direction. Now it tells me I need to flatten out a little bit. All right, so as t gets really big, all of my solution curves are directing me towards my equilibrium, so this is stable. And then let's look at this one. So these two differential equations are very similar. The only difference here is that this one has a negative and this one does not. And that k is just a constant that's being multiplied times h minus 2. Okay, so if I pick an initial condition here, so maybe I start here, and it tells me to head off in this direction. So I do that, and now it looks like I'm getting steeper. Okay, so that looks like I'm heading away. Let's pick another initial condition. How about right here? So this tells me to head off in this direction, get a little steeper and a little steeper still. All right, so definitely still going away. Let's try here. So if I head off in this direction, it tells me to get a little steeper still. All right, so it looks like no matter what I do here, I have headed away from my equilibrium. So this is unstable. Okay, so for obvious reasons, probably, the stable is sometimes referred to as an attractor and the unstable as a repeller. Okay, and then let's look at how we would actually figure out that that's h is equal to is our equilibrium solution. And the way that we do that is we take our differential equation and we set it equal to 0, and then we solve. So this k is some sort of non-zero constant, so it doesn't really matter in the solution. And then I have h minus 2 is equal to 0, and if that's true, then that means h is equal to 2. And the same thing will happen over here. So we set this thing equal to 0, we find that h is equal to 2. So that gives us our equilibrium solution. All right, so let's try this out. Find the equilibrium solution to the differential equation dp dt is equal to negative 50 plus 4p and determine whether it's stable or unstable. So I'm going to set this equal to 0. I get 4p is equal to 50, which tells me that p is 50 over 4, which is 12.5. All right, and now I need to determine if this is stable or unstable. So what I'm going to do is draw a quick little graph here. So here is T, here is P, and I'm going to put this equilibrium solution on here. So this is the 12.5 that we found. And then I'm going to look and see what happens both above and below. So I start by going above. So I'm looking at values of P that are greater than 12.5. So let's do, I don't know, maybe P is equal to 15. So if I do that, then dP dt is equal to negative 50 plus 4 times 15, which gives me a positive 10. And 10 is greater than 0. So I know that if my P is greater than 12.5, my derivative is going to be positive. And if you remember back to Calc 1, that means that the lines here are increasing. Okay, so I'd be looking at all kinds of positive slopes here. We can do the same thing with P is less than 12.5. So let's consider maybe P is equal to 10. So I get negative 50 plus 4 times 10, which gives me a negative 10. So that's less than 0, which tells me I'm decreasing everywhere below my equilibrium. So this side's doing this side is doing this. That sure looks like we're going away from our equilibrium if P is 12.5. So I would classify this as unstable. Okay, you're certainly also welcome to make a quick sketch of the slope field. That's another way of doing it. Either one of these approaches would be totally fine to determine whether it's stable or unstable.